All right, welcome to the Explainer. Today, we're opening up a Mons AI journal to decode a highly technical yet absolutely crucial topic in modern machine learning, evaluating transferability estimation in your model training workflows. Look, if you're involved in training AI, understanding the efficiency of your pipeline is everything, and that is exactly what we're going to unlock today.
Okay, let's dive into this. Imagine spending massive amounts of time, money, and compute power transferring a highly capable pre-trained AI model to a new task. You're expecting great results, but then you find out it actually performs worse than if you had just started entirely from scratch. That phenomenon is called negative transfer, and it is a massive headache for AI researchers. So, how do we prevent it? How can we know a model will actually succeed before we commit all those resources to it?
Here's our roadmap for the Explainer. We'll start with the Transfer Learning Challenge, then enter Transferability Estimation. From there, we'll cover Approach 1, introducing LEEP, and Approach 2, introducing OTDD. Then we'll put LEEP versus OTDD, and finally wrap up with the final verdict. So Section 1, the Transfer Learning Challenge. In modern machine learning, transfer learning is incredibly popular. It's kind of like a trained pianist having a way easier time learning to play the organ than someone who's never even touched a keyboard. The whole goal is to take pre-trained models, ones that have already learned general features from massive datasets, and adapt them for new, specific downstream tasks. It's super efficient. But efficiently evaluating the transferability between those different datasets, well, that's still a huge open research topic. We really need a reliable way to predict success. Which brings us to Section 2, enter Transferability Estimation. Transferability estimation is basically our mathematical filter. It's the act of evaluating these pre-trained models for transfer learning so we can maximize our target task performance and, crucially, stop that dreaded negative transfer. It helps us correctly select a pre-trained model so we don't accidentally end up going backward in performance. Moving to Section 3, Approach 1, introducing LEEP. LEEP stands for Log Expected Empirical Prediction. This was proposed by Nguyen and a team of researchers from Amazon Web Services and Facebook AI back at the ICML conference in 2020. Now, LEEP measures transferability by evaluating the log likelihood of the correct prediction on the target dataset. I know that sounds a bit complex, but it's fundamentally just about using predictive probabilities. And this brilliantly illustrates how LEEP actually functions under the hood. It uses a predictive distribution based on two conditional probabilities. Step 1 calculates the probability of a dummy label based on the categorical distribution of the model that was trained on the source dataset. Then, Step 2 looks at the conditional density of the target dataset's actual label given that dummy label. LEEP integrates these two steps over all possible dummy labels to create a highly accurate predictive distribution score. All right, Section 4, Approach 2, introducing OTDD. OTDD is short for Optimal Transport Dataset Distance. This one was proposed by Alvarez Mellis and researchers from Microsoft Research at NeurIPS, also in 2020. Now, the core philosophy of OTDD is entirely different from LEEP. Instead of looking at model predictions, OTDD measures the actual distances between the datasets themselves using mathematical optimal transport. The logic here is highly intuitive, right? A smaller optimal transport distance between your source and target datasets simply indicates better transferability. To de-jargon this a bit, OTD calculates this optimal transport distance by breaking it down into two specific subdistances. First up, it measures the distance between the raw feature vectors of the two datasets. Second, it measures the distance between the labels of those datasets, where each label is represented by the distribution of its associated feature vectors. It just combines these two to give you a total dataset distance. Let's get to the fun part. Section 5, LEEP versus OTD. Now, what's really interesting about this slide is the prerequisites. OTD seems to have a massive initial advantage here. See, LEEP requires you to actively train a model on the source dataset first, just to generate those dummy labels we talked about. But OTD, it doesn't require a trained model at all. It literally only needs the feature label pairs of the two datasets to start calculating distances. So on paper, OTD sounds like the clear winner, right? Well, here is the major plot twist. When we look at computation, OTDD is incredibly expensive. To measure that dataset distance, OTDD relies on heavy Wasserstein distance mathematics. This forces researchers to rely on very coarse approximation algorithms, like assuming a Gaussian distribution just to make it run, so it loses precision. LEEP, on the other hand, is phenomenally cheap and fast. Because you already have a trained model, it only requires one single iteration of inference on the target dataset to grab that dummy label distribution.
Theory and computation are one thing, but how do these actually perform in practice? Let's check out the experimental validation and statistical correlation straight from the source papers. Both of these research teams validated their approaches on several transfer learning tasks to see how perfectly their scores correlated with actual target dataset performance. And wow, LEEP achieved a massive 0.94 correlation coefficient. Now, when you're measuring correlation here, the closer you get to 1, the better and more accurate the measurement is. LEEP hit this stellar 0.94 score when transferring from massive image datasets like ImageNet or CIFR10 over to the CIFR100 dataset, just highly accurate. Following up, we look at OTD's best result, which was an impressive negative 0.85 correlation. Now, keep in mind, OTD measures distance, so a correlation closer to -1 is actually what you want. It means a smaller distance equals a smaller relative drop in test error. They hit this negative 0.85 mark when transferring from an augmented MNIST dataset to the USPS dataset. However, there is a catch. When the researchers tested OTDD transferring from the MNST dataset without any data augmentations to the USPS dataset, its correlation plummeted to just negative 0.59. Because of those coarse mathematical approximations it has to rely on to save compute time, OTDD's accuracy can really drop off depending on the exact nature of the datasets you're using. Which brings us to Section 6, the final verdict.
So the crucial point is this. Both of these approaches represent a massive shared victory for AI researchers. Yes, they have their trade-offs. LEEP needs a source model but runs super fast, and OTD needs no model but runs heavy mathematics. But neither approach requires you to go through the grueling process of retraining a model on the target dataset just to evaluate its transferability. They both act as an incredibly efficient filter to stop negative transfer in its tracks.
Which leaves us with a critical question for your own machine learning workflows. With compute costs rising literally every single day, which estimation approach are you going to choose? Are you going to leverage an existing source model for a lightning-fast LEEP estimation, or rely on pure dataset distance mapping with OTD? Understanding these frameworks is exactly how you build more efficient, powerful AI. Thank you for diving into this explainer with me, and keep learning.